Hi, and welcome to my series on production grade systems development. My name's Dave Orme, and I'll be your guide as I walk through today's episode which covers our data and APIs. If you're new to this video series, I encourage you to go back and have a look at the previous videos, which will give you a lot more context leading into this one. If you want to follow along, open your browser to github.com/davidorme/speaker. Otherwise, if you're more comfortable, just watch along and I'll take us through all the code in the video. In a previous video, we covered the importance of modeling data in our Postgres database. Then we looked at using the SQL-C tool to get the data out of our database into our application layer, converting it from Postgres data types to Go data types. In this video, we'll be covering how data is represented in our API layer and how to model it, how to validate it. Our API is one of the most important parts of our system. In essence, it's the interface for our system with the outside world. So a key part of it is modeling the data as it flows through our API. In an earlier video, we briefly discussed how we're going to use JSON as our data format. JSON data is used in three key ways. First of all, for our API requests coming in. Secondly, for the responses flowing back from our APIs. And lastly, for data that we publish as events onto our message bus. So we've already established that JSON's a great data format. The reasons being, it's human readable. It's just plain text. You can easily look at it and eyeball it. It's lightweight, relatively small and fast to parse and generate. It's also language independent, which is important for our customers that might be calling our API from another programming language. It's structured, so it's able to represent general types of data. So objects which contain key values, also arrays, nested objects, and so on and so forth. And it's widely used. It's pretty much the de facto standard for REST in modern web APIs. Okay, great. We're going to use JSON to represent data, but how do we provide our own specific kind of JSON that's relevant to our system? This is where JSON Schema comes in. JSON Schema allows us to provide another layer of semantics and syntax across standard JSON. So we can very precisely define what our API requests, responses, and messages look like. Using a JSON schema compiler, we can validate those things. So we can check that a piece of JSON matches a JSON schema structure or not. Key to any good system is that it's well formed, consistent, and predictable. It's good to remember the timeless wisdom. Test everything and hold fast to what is good. So, we'll be using JSON schemas to define our requests, responses, and events. We're not going to go quite as far as defining an open API specification for our API, but that's certainly possible because we're using the same building blocks that OpenAPI uses for generating its schemas. So what tools will we use in our application to deal with JSON and JSON schema? Go has good support for JSON, so that's kind of an easy tick. The standard library contains a package that allows us to marshal and un-marshal JSON to and from Go structures. As far as JSON schema, we'll be using a third-party tool. It's at github.com/santosh-takuri/JSON schema. This is both a library that we're going to use in our application and also a CLI tool, and we're going to use both. The CLI tool will be used at our build phase just to check that our JSON schema files are well formed. At runtime, we'll use the library to validate that incoming requests are valid according to the JSON schema. By having the library do it, we're going to save a whole heap of time because the JSON schema specification allows us to define programmatically a whole bunch of validation rules. So we just have our schema, we ask the compiler to validate the input against the schema, and it will tell us if there's any validation problems. So in effect, we're moving the validation from code into configuration. Writing less code's always a good idea. So this fits well with our philosophy. Let's start by looking at a JSON schema file. Open up the request for adding stock in schemas/stock-add.request.json. So the first line, which is $schema, points to the JSON schema version, in this case, the draft 2020-12. This is the latest version of the JSON schema standard, and it dictates what the JSON schema compiler will allow and not allow. Next, we have the $ID field. This is a unique identifier or URI for the schema, so it can be referenced elsewhere in the system. Then we have the human readable title for the schema. Next, we have the type. In this case, it's an object. So JSON data must be an object containing key value pairs. Following that is the properties. This lists the valid fields inside the object. In our case, we've got ProductSKU, which references another JSON schema, which is github.com/davidorum/beaker/schemas/ProductSKU.json. So the ProductSKU field must follow another schema that defines valid SKU values. Next, we define the quantity. Its type is integer, is a minimum value of 1, and the description is a helpful hint for someone reading the schema to know how to use it. Following that, we have the required array of fields. It contains ProductSKU and quantity, which indicates that both fields must always be supplied when you're supplying this JSON. Beyond that, we have additional properties false, which indicates that no extra fields beyond those two are allowed. So in summary, the schema defines a stock-add request that must include a valid ProductSKU field and a quantity which must be a positive integer. And you're not allowed to provide any other properties. We don't yet fully understand what the ProductSKU definition is. It's defined by that ref statement that we talked about. So that tells the JSON schema compiler to look elsewhere for the definition of ProductSKU. So let's open up the schemas/ProductSKU.json and look at how that's defined. So it starts off very similarly, providing a schema, which identifies the JSON schema standard version, a unique ID, and a title, and then a type. The type is string, which means that a valid string must be provided, not a number or an object. Next, the pattern is defined. That's a regular expression that defines the valid characters, letters, digits, underscores and hyphens that are allowed. I noticed here while I was writing this video that this is a little bit incompatible with what we've done at the database level, where we only allow lowercase characters. So that's something I'll have to correct at some point. Following that's the description that explains the field and its constraints, which is useful for a documentation task. Next, we've got the minimum and maximum length of that string, so between 1 and 64 characters. Following that, we provided a bunch of examples. This is to help someone reading the schema give them an idea of what some valid ProductSKU values might be. In summary, this file defines a valid ProductSKU. It's a string between 1 and 64 characters, and it's limited to the valid set of alphanumeric characters, underscores, and hyphens. It must be between 1 and 64 characters long. That's great, but how does the JSON Schema Validator know to link the two schema files? There's a big clue in the schema-lint makefile target. When you run make schema-lint, it iterates over all of the JSON files in the schema directory, passing each one to the JV command line tool. The assert format option tells JV to check the file being validated is correctly formatted as a valid JSON schema file, not just valid JSON. The -- draft 2020 option specifies that the JSON schema version must match the draft 2020-12 to validate. Passing --map with http github.com/davidoram/beaker/schemas equals schemas creates a URI mapping so that when the schema references something like ref http github.com davidoram beaker schemas ProductSKU.json, the JV command knows how to resolve that reference locally from the schemas directory instead of trying to fetch it over the network. So when we run make schema-lint, it should say all schemas are valid. But let's double check to make sure it picks up an error. Let's edit the schema's stock-add request and introduce a typo in the ProductSKU reference. When you rerun make schema-lint, it should return an error. So how do we perform checks inside the API at runtime? It involves the following steps. First, we're going to create a JSON schema files. Then we set up the JSON schema compiler. We perform validation of the raw JSON. We define Go structs that match the schema. And then if validation works, we're going to marshal the raw JSON into the Go structs so the application now has that data available to it. So let's go through those steps in a bit more detail. We've already seen the JSON schema file definitions, for example in schemas/stock-add.request.json. We've factored out any common types into their own files so we can reuse them, like we did for schemas/ProductSKU.json. Next, let's look at how the JSON schema compiler is constructed. If you open the internal/utility/schemaloader.go file, we're going to walk through the new JSON schema compiler method. It takes a context, that's unused, my bad, and a schema directory, which is the folder that holds all our schema files. We pass that into the new loader function, passing a map from URL prefixes to the directory that holds the schemas with that same prefix. The loader's job is to resolve schemas as they're being validated. When the schema compiler needs a specific schema as identified by its ID, it asks the loader to retrieve it. Our loader will load application schemas from the schema directory, but then it will go to the HTTP loader to retrieve schemas that it can't resolve, and that will retrieve them across the internet. Then we create a file prefix loader which checks if the URL prefix matches one that's mapped into our folder. If so, it loads that from disk and returns it. If no match is found, the request passes on to the JSON schema URL loader. So if it's a file, it will use the file loader. It simply loads the file from the file system. If the schema is HTTP or HTTPS, it delegates to the HTTP loader, which uses an HTTP GET to retrieve the file from the internet and return it. We need a little sidebar here to talk about caching. You might be thinking, I don't see you caching any of these requests. That's right. I always avoid caching until it proves to be a problem. Why? Caching's hard. Caching's hard because you trade correctness for speed, and keeping that trade fair is tricky. You need to know when the truth changes, that is, you need to invalidate the cache. You also need to know how long to cache for, or the time to live. In a distributed system like the web, there are many layers of caches. All this makes for is a tricky debugging scenario. So I always like to verify that what I've got is fast enough before I start looking at caching solutions. Do the simple things first, and God will handle the impossible refactors. Back to the new JSON schema compiler function. Now that the loader has been created, we create a new compiler and attach the loader. Then we call assert content, which means that the schema says the field should contain a specific type of encoded content, like for example base64 data or a certain media type. I want you to double check that it actually does. Assert format means, for example, if a field says it must be an email address, then make sure it looks like one, not just any old string. Some JSON schema compilers treat these things as hints, but don't really enforce them. And our goal is to be as strict as possible with all of our inputs. Lastly, we tell the compiler to use the latest draft version of the JSON schema standard. When we want to use the compiler, we'll call the ValidateJSON function. It's in internal/API/request.scope.go. The first few lines capture telemetry data. We'll talk about that later. Incidentally, capturing precisely how long an operation like schema validation takes allows us to make data-driven, informed decisions. If the idea of a caching scheme comes to you, you can look at the telemetry data and gauge exactly how long doing this work is taking and decide if you need to optimize that part of the code or not. Don't be fooled into thinking that faster is better everywhere. Sometimes you want to trade off complexity to gain a millisecond or two, and it might not actually be worth it. You might spend your time better looking for optimizations elsewhere. Right, we check if RS has error. We'll come back and talk about that in the future. Next, we check if the JSON data is empty. That's immediately an error. If the compiler hasn't been passed, that's also an error. Finally, we get to ask the compiler to compile a schema for us based on the schema name that we asked for. Again, this is a potential place you could cache things, but I don't need to, so I keep the code path nice and simple. If the schema is nil, that's an error. But if not, we use the function that the library provides to un-marshal the JSON again, checking for errors. Now we get to the important part. We call schema.validate passing the data. This takes the JSON, validates it against the schema, and returns an error if it doesn't comply. It's as simple as that one API call to perform all the multitude of validations that JSON schema can apply. This means I can change my schema file to include a new validation. I don't have to change any code. When the validation runs, it picks up the new schema file, will apply the new validation. If you want to know more, go and have a look at the JSON Schema website. So we've moved our validation from code into our JSON Schema files. But what's the trade-off? The error handling might not look as nice as a custom error message because the validator generates the error messages itself and we just have to use them. So assuming the incoming data has passed through JSON validation successfully, how do we use it inside our application code? That's actually pretty simple. Go provides a way for us to define structs and then have the JSON marshaled straight into those structures to get the data in a convenient format. Let's take the example of looking at this stock-add request. The Go structure defined in file schemas/stock-add.request.go, and it's super simple. Open up that file and you'll see near the top we define a constant representing the schema, stock-add.request schema. We'll be using that later in the application code when we ask the library to validate some JSON against that specific schema. Next, it defines the stock-add.request struct, which contains the same fields we defined in the JSON schema file. What's important to note here is the use of structure tags. They are the notations inside the backticks to the right of each field, and they tell the Go standard library how to map JSON values into the struct, a process known as un-marshaling. And also from that struct back out to JSON, a process called marshaling. You can learn more about Go struct tags online. It's something your code can use to attach metadata to struct fields. That can be extracted and used at runtime. Once we've got the JSON data into a Go struct, it's ready for our application to use. Once our application's finished with the data, we need to transform the Go struct back into JSON and return it to the caller. We will populate a Go structure to represent API responses that go back to the caller. If you open up schemas/stock-add.request.json, you'll see the data that we need. That data will be marshaled from the Go struct to JSON and returned in the response. This is all done through the standard library function JSON.marshal, which uses the same struct tags that are used by the un-marshalling process, but this time it converts the data from the struct to JSON representation. This structure shows a real interesting feature of Go struct tags. You'll notice that the ProductSKU quantity and errors are all pointers, and the struct tags contain the annotation emit empty. The emit empty directive will tell the marshalling process to skip that field if it's empty or nil. This will become more obvious why we need to do that when we look at the guts of the API handlers in a later video. We utilize this to make our life easier. Let's take stock of what we've learned. JSON is our chosen data format for requests, responses, and messages due to its textual nature, lightweight, and multi-language support. JSON schema is used to validate, document, and enforce the structure of JSON data for our requests, responses, and events. Go's built-in JSON support, we're going to leverage that for marshalling, un-marshalling, while the JSON schema library is going to support validation both at build time and at runtime. We've moved validation logic from being in Go code to being inside our JSON schema files. This reduces our amount of code we have to write, and it improves general maintainability. Thanks for listening, and remember, iron sharpens iron and one man sharpens another. Hit the subscribe button if you want to be notified when the next video is out. In the next video, we'll be discussing telemetry. I look forward to seeing you then. Thanks for watching.